Those are the results from last semester. You don't want to see those. Okay, so here's my results from today. So let's see. Let's compare you. Who's the best class? It's you, of course. Oh, wait a minute. You're only at 88%. And some class got 100%. It's because I goaded them yesterday. I showed them this yesterday, and they were actually behind you yesterday, and they said, no, we must win. And they only have 10, so it's easier for them to win. So the three of you who haven't done it yet, maybe you don't care about extra credit, that's fine, but you could help us be as cool as the Calc1 students. All right, so why are we doing all of this business with the series? That's what you want to know. Well, here's a good example. So let's take a look at this. This is similar to what you're going to have on one of your homework problems at least, and then we'll see if we can wrap things up. Today's going to be a little bit shorter than normal for two reasons. Number one, I don't have a quiz for you because we didn't have, well, you know the drill is I have homework, the quiz is similar to homework, and so on. Secondly, I had planned to do the whole lesson yesterday that I'm finishing up today, so I don't want to drag things out too much. But I do have some other information after we do this. So what is this? What is this? Does anyone recognize that out of curiosity? Let me draw the curve. Let me do this. You'll recognize it once I sketch it. So that's a famous curve there. I hope I've got that written correctly. We're going to find out in a minute because we're going to actually compute that. So here is what that curve looks like. If I do y equals 1 over radical 2 pi times e to the negative x squared over 2. So that function looks like this. Now you know what it is, right? Maybe, some of you? It looks familiar. Okay, I'll put even some other little nuggets on here. We have this here. Turns out there's a point of inflection right here at -1 and another point of inflection at 1. That's where the curve stops being concave down and begins being concave up. Let's see, 2, -2. There it is. So this is the standard normal distribution. So this is a normal distribution. It's normal where the average is 0 and the standard deviation is 1. So this is kind of the quintessential normal distribution. So when you take statistics and you learn about normal distributions, there's the function. That's the actual function for the normal distribution. You can shift it left and right, you can stretch it out, but that's the function. Okay, so you remember maybe if you've taken stats that one of the things that you did was you computed the area under the curve because the area under the curve corresponded with a probability or a percentage. So this is the area that I want to compute here. It's just the area between -1 and 1. And you can see I've got it set up correctly. Since we're in calculus class, we can do this using calculus. We don't have to go to Excel or we don't have to use our calculators. We can do it using calculus. Well, the first problem that we're going to run into, and it's a pretty big problem, is the problem of doing the antiderivative of e to the negative x squared, or negative x squared over 2. In my first class, I have students who are very keen on using Desmos or some sort of online calculator, and I tell them, you know, you're not going to be able to do that on your exam, and they say, oh yeah, we know, but we don't care, we still love it. So let's go ahead and go to one of those. Is Desmos, is that a thing? I don't know, I think they've used that, Desmos integral. I'll just type this in, search for it. Definite integrals? Oh yeah, okay, I'll pull this over and see what it does for me. Oh, but that's a function. Does it have the antiderivative? No, it doesn't. What function is it, or what website do you go to get math done, to do calculus? Symbolab? Symbolab, did I spell that right? Symbolab integral. Oh, it's right there. That's what I want. Yeah, I want one that actually computes the antiderivative. Yes, this looks right. Okay, whatever it is, yeah, let's go ahead and do this. I could probably also, I could just go to ChatGPT, because ChatGPT will do it, won't it? No?
ChatGPT sucks at math.
Actually, one of the kids, I forget what he had some sort of AI tool that actually was pretty good. But yeah, I've tried to use ChatGPT for like coding, and it does some weird things sometimes.
It can do coding, but it can't do math.
Well, when I'm trying to get it to code math, that's the problem. Okay, well, let's do this. We have the integral. I need to shove this in here. All I really care about is this. Is it exp, do you think? Let's find out if exp is the, oh, maybe it's e. Let's do e. E to the, let's see, in parentheses, negative x squared, whoops, over 2. Oh, come on. There. Is that all in the, that's all up there, isn't it? Okay, let's do it. Go. Go, go, go. Wait a minute. What is that? What is ERF? I've never heard of ERF. Actually, I've heard of ERF. But what is ERF? Let's see, does it tell me what ERF is? It just all of a sudden says, use the non-elementary integral, ERF. Okay, I'm going to have to Google ERF now. What is ERF? Maybe I should do ERF of x, question mark. Let's do that. Oh, I guess I'm not Googling, am I? I'm DuckDuckGoing, but that's because I'm concerned about my privacy, apparently. Okay, ERF, the error function. We'll go with Wikipedia. That sounds good, doesn't it? Okay, it says that the error function in mathematics is the Gauss error function, denoted as ERF. And the definition of ERF is, wait a minute, isn't that exactly what I'm trying to compute? So basically, this is like a circular thing. It says the definition of, oh, you can't see, it's up there, yeah. Oh yeah, and there it is, statistics. It shows up. But anyway, yeah, so here's what we run into is when we try to do this, first of all, there is no elementary function antiderivative for this thing. And so we just make something up. Mathematicians just say, oh, we're going to call it ERF because we have nothing else that we can do with this. But I still want to know the value of this, and I can't compute ERF of -1 or ERF of 1. So what we're going to do this is I'm going to rely on a power series. So let us remind you of the power series representation of e to the x, the Maclaurin series. So this is n equals 0 to infinity of x to the n over n factorial. I think I mentioned that I'll put this on the exam so you don't have to have that memorized, although if you use it enough times, it will become memorized. I remember, I don't know if you've ever had this experience, but for some reason this popped up in conversation the other day. I can remember making a cheat sheet for myself. I was a cheater. No, I was not. But I was worried about a particular exam. So I made a cheat sheet, and I stuck it in my jacket pocket like this, because I dressed like this in high school. Anyway, so it was right there. It was at the ready. I was ready with it, this little piece of paper. I got to the exam. I didn't need it because I had made the cheat sheet. I'd memorized all the stuff that I'd put there, and I was like, well, guess I don't need to cheat. So lesson learned is that if you practice something enough times, you'll have it memorized and you'll be good with it. So memorize that, but I'll put it on the exam anyway. Okay, so there's e to the x. I need to know what e to the negative x squared over 2 looks like. Well, that's easy enough to do. That's going to be n equals 0 to infinity of negative x squared over 2 to the n over n factorial. So you know the drill here is that what we do when we're doing Maclaurin series, Taylor series, is we have a series that we know, and then we want to just modify it a little bit. Let me clean it up a bit. So this thing looks something like this now. We have -1 to the n times x to the 2n over 2 to the n times n factorial. Now we have a couple of options now as to what to do, because the goal is to do this radical, this integral. By the way, if you know the empirical rule, you already know the answer to this question. Well, I hope maybe. We'll find out. And that's why I'll find out pretty quickly if I've written down my normal curve correctly, the Gaussian distribution. So anyway, so here's what I'd like to do. Dx. I just moved that constant out in front of the integral. So what I could do, since I don't know the antiderivative of that function in there, that e to the negative x squared is the big problem. So the 2 is not really a big deal, the x squared over 2. That's not, you could substitute that out of the whole thing, but it's that x squared that's the problem. So what I'm going to do is I'm going to change this to the power series. Not only that, I don't want to have to integrate this whole power series and worry about the sum. You could. That it's not that big of a deal, especially with this particular power series. I could just integrate it term by term. Basically, you would get x to the 2n plus 1 divided by 2n plus 1. You know how it works. But I'm going to go one step further, and I'm going to say that that is going to be approximately equal to this. Let's see. I'm going to basically just decide that I'm not going to use all of the terms. And so we'll start with 1. That's the 0th term. Let's see how far I'd like to go. Maybe 4 terms? Let's do 4 terms. So there's 1. We have minus x squared over 2. That's the n equals 1 term. So notice what I'm doing is I'm writing down, basically it's going to be the Taylor polynomial. So this will be the Taylor polynomial, degree 8, I guess, if I'm using 4 terms. But it'll be a Taylor polynomial. And then I'm going to plug in n equals 2, and I get x to the 4th over 8. You can double check my math. When n equals 2, it's 2 squared times 2, which is 8. And then one more term. I guess this is the 6th degree. I'm just going to do 4 terms. So this will be x to the 6th. It's minus because when n equals 3, you get a negative there. So minus x to the 6th over, what is this going to be here? 2n in factorial. Sorry, I just had a little brain freeze. It's going to be 6 times 8, 48. Because that's 2 to the 3rd over 3 factorial. Or 2 to the 3rd times 3 factorial. And that's it. So this is tantamount to doing the power series, integrating the entire power series, and then just using the first 4 terms of the integrated power, which is the power series for what I'm interested in. So that's what's happening here, just so you know, because this is going to matter when we ask the question of, if we do it this way, if we don't do the entire series, what's the harm? We're going to find out what the harm is momentarily. Well, let's see how close we are to the truth, or let's see what the truth is now. So we can integrate this term by term. So 1 over radical 2 pi. You can all do this. Whoops. Don't forget that after you do your antiderivative, I don't want to see that symbol anywhere, that integration symbol. Okay, so this is x cubed over 6, x to the 5th over, 32, x to the 7th over whatever this is, 48 times 7, evaluated from -1 to 1. 1 over radical 2 pi. The pi is under the radical there. Okay, give me a second here. I'm going to use a trick of that works when you have an odd function, or rather, it works when the function that you're integrating is even, and the interval is symmetric about the y-axis. Yeah.
It should be x to the 5th over 40.
Oh, you're right. 40. Thank you. 32. What am I doing here? Yeah, 40. Thank you. Yeah. Anyway, so the trick I'm going to use is that once I plug in the number 1, the number -1, since this is symmetric about the origin, this function, will be just the negative of what I get when I plug 1 into this, which means that when I subtract it, I'll just get 2 times whatever I get when I get the 1 there. So you can actually plug in both limits if you want to, but I'm not going to. I'm just going to use this symmetry argument. So 1 over 48 times 7. And then at this point, I'm happy to pull out my calculator and use it because I don't want to have to do this in my head. Apparently my mathematics, my head is not working quite right this morning. There we go. Let's clear this out. So let's see, this is going to be 1 minus 1/6 plus 1/40 minus 1 over the quantity of 48 times 7. And that equals 0.8553. I'm curious if this will do the fraction. Oh, it does. Wow. Okay, so this is 2 times 479 over 560, for what it's worth. At least according to my calculator, it's 479 over 560. Okay, so multiply that times 2, and then we're going to divide that by the square root of 2 times pi. Don't forget to put the pi inside the square root. Oh no, my calculator just, what? Okay, finally I got it. 0.682476. Okay, I'm happy, because that's what I was hoping I'd get. So I don't know, does anyone remember the empirical rule from statistics class? So the empirical rule, just to remind you, if you've had stats, if you haven't, it's fine. The empirical rule says that in any normal distribution, if you go 1 standard deviation to either side of the mean, you should expect to have about 68% of the entire population there. If you do 2 standard deviations, you should find 95%. Maybe it's jogging memory now. 68, 95, 99.7%. So anyway, that's sort of verifying it using mathematics. Okay, so this is 68% or 0.6824. How close are we now? How close are we to the truth? Well, what we've done here is we've basically taken a Taylor polynomial and truncated it. No, that's dumb. What I said was dumb or redundant, because Taylor polynomials are already truncated. It's a truncated Taylor series. So we've got this Taylor polynomial. We want to know what is the harm that we've done. Well, if you remember, the harm that you've done is going to be equal to, here we go, this is the error. So this is essentially what I have here is I have the Taylor polynomial of degree 7. Yeah, it's the 7th Taylor polynomial. And what we're looking for is we're looking for the remainder, which is the actual function value minus the Taylor polynomial. And by this function, I don't mean the Gaussian distribution. I mean the actual integral, the actual antiderivative. That's what I'm interested in, is how far off will that antiderivative be on this range. So what we can do is we're going to do the this r sub 7, which ends up being the 8th derivative, m, I'll do it the right way here, m times x minus a to the 8th over 8 factorial, and that m is the maximum of f8 on your interval. Okay, so we need to know what f8 is for this thing. Maybe I don't want to know. Oh, actually it's not terrible, because we have the power series here, so we should be able to figure it out, because this is the power series. What is F8? Okay, how about if we do it this way? You know what, I'll just do it on Desmos. The 8th derivative, I don't want to have to do it. So I've got myself into this problem here, so I'm going to have to do it. So does this do derivatives? Is there a derivative place? Calculus, derivatives, calculus, derivatives. You got it. Derivatives. Okay, d over dx. What if I do d superscript 8 over dx 8? Does it understand that? Dx 8. Let me see if it understands that sine of x. I'll just do this as an experiment. The 8th derivative, is that what it's doing? Okay, let's hope. Let's try 2x just for fun. Sine of 2x, we should be multiplying by 2 to the 8th. Yeah, okay, it does understand my, okay, that's all I wanted to check. So I need the 8th derivative of e to the negative x squared over 2, oops, x squared over 2. Did that do it? Okay, let's try this. 8th derivative. It's going to be some, because you have to use the product rule. That's why I'm trying to avoid it. Okay, that's what it is. Lovely. Okay, so what's the worst case scenario with this thing? The very worst that this could be. So notice something about this. Yeah, I thought it would be easier than this, but it's fine. Notice something about this, that what you have here is you have this e to the negative x squared over 2. And that's going to actually, that e to the negative x squared over 2 has this shape. The very worst case scenario is when x equals 0. That's the highest point. And so when x equals 0, most of this is going to be 0, and it's just going to be this 105 here. Even if you just took all the coefficients and added them up, because we're dealing with numbers between -1 and 1. Maybe we could do that as a stopgap, since I'm kind of waving my hand here, faking this out a bit. But x is always between -1 and 1 on my interval, and so the worst case scenario is this is 1 and x is 1, which this would not be 1 if x was 1, but we're getting a bound. And let's make these all pluses instead of minuses, even though that doesn't make a lot of sense. So let's see, we've got 105, 420, 210, so we're up to about 735, and then you got 28 and 1 there. If you add it all up, we're less than 1,000. That's what I'm trying to get at here, is that the very worst case scenario, the biggest that could be, is less than 1,000. So let's go back to my little estimate here. So my estimate isn't going to be perfect, but I'm going to just say this, that it's going to be less than this. It's going to be less than 1,000. It's going to be less than 1,000. Now x minus a, what is that? Well, the center is 0. And so the worst that you could get is x equals 1 minus 0 to the 8th power. And then 8 factorial is just 8 factorial. 7 factorial is 5040. So 8 factorial is 4,320. Is that 8 factorial? Well, anyway, you can see here that this is going to be on the order of 1/40th. 1/40th, that means that at least about 2 digits. And that was overestimating that maximum. So my estimate is pretty darn good, is what I'm saying here. So anyway, let's take a peek here at homework, because I want to make sure that I've kind of forgotten what the homework's like. So give me a sec, and we're going to take a look at the homework and make sure we cover whatever the homework has on it. So I'll pull this up here, Calc2, and where are we? Down at the bottom. Oh, and I need to show you something as well about the website, but not yet. Let me do this first. To preview this. Okay, here we go. This is the last of the Taylor and Maclaurin series homework, the F11. That's better. Okay, so you'll notice that I start off with the same matching. It's the same one you had last homework. And the only reason for that is because I thought it would be nice if you had this front and center, since we don't have a physical textbook. I wish we did now. I regret not having a physical textbook, but we don't. So here now you can see, you can have these right here. So I guess this one, yours is going to be shuffled different from mine. So my first one is A. You can figure out the rest of these. This next one is B as well. Wow, it's right in order. Sine? No, the next one, sine is D. But anyway, you can figure that out. So you have those ready for you to use on things like this. Okay, so here's the deal. You have, this is very similar to what we just did, but it's a fourth degree polynomial up there, but you're going to do the exact same thing. So we want to be able to get a Maclaurin series for the polynomial degree 5 for this thing. You might say, wait a minute, what in the world does that mean? Well, what this means is that you're going to do the antiderivative of this. That's what it means. And then you're going to subtract off 0, but don't worry about that right now. So basically that's just looking for the antiderivative of that. So you make the Maclaurin series for this function, do the antiderivative to get this. There is the constant issue. What is the constant going to be? Let's see. What is the constant here? Oh, they have no constant. So I guess you don't have to worry about a constant. You saw how simple it is. So degree 5, and then they want to use this to estimate this value. You can do that yourselves by actually plugging in that value to this series. Okay, so that's pretty easy. Okay, finding sums of series. We did this yesterday, didn't we? Something like this. So let me just give you another hint, remind you how to do this since it's been a whole day. So what you want to do is you want to figure out what that series looks like. So going back, you'll notice that that looks similar. Hold on a minute. There we go. Where's my mouse? There it is. Okay, so going back up here, that looks similar to this series. So that top one, letter A, compare letter A to this here. So that's going to look like that series. So let me write it here. Give me a sec. 1 to the n, 9 to the n minus 1, over 2n factorial. Okay, so now I'll show you what I've done. So what we're going to do is we're going to compare this to this series. So this one is negative 1 to the n, x to the 2n over 2n factorial, which is the cosine. So you'll notice that this looks suspiciously similar. The big difference between these two is instead of x to the 2n, I have 9 to the n minus 1. So what we're going to have to do is we're going to have to do a little bit of algebra, not much. All of these that I saw, at least the versions that I saw for all of these, should work out relatively nicely. So here's what I'll do is I will rewrite this like this, 3 squared to the n minus 1, because 9 is 3 squared. And that equals this. I probably don't need to write all these steps down because some of you already know what the answer is going to be, but I'm going to do it anyway. So I have 3 to the 2n minus 2 over 2n factorial. I'm almost done. Like I said, you're probably not going to write down all of these steps when you do this. I'm just doing it because I want to make sure that I don't make anyone uncomfortable with the pace. Okay, so make sure that you understand going from the 9 down to this with the 2 3s. So I'll pause, make sure you understand that. If you don't understand a step, let me know. But it's basically we're doing some algebra manipulating this expression. Okay, let's do it. Now that we've got it like this, you can see that the big difference, now there is no difference. The only thing is instead of an x, I have a 3. So since this is the cosine of x, this will be the cosine of 3. So that's going to equal the cosine of 3 times 3 to the negative 2. Which, if you want to be fancy, you could do it this way. And I think that's the way that they want us to type it in. Let's check. I'll just, instead of typing it, I'm just going to click it. Yeah, 3 to, oh, yeah, I'm pretty sure that they would accept 1/9 cosine of 3. So anyway, you're just comparing these to the Maclaurin series that we're familiar with. Same thing here. Hopefully you recognize this one. If not, it is one of the ones up there, just with a slightly different, the exponent there is a little bit different, but you can manipulate that algebraically. This one is similar to one of the ones up there. Here, let me identify these. This one is e to the x is related to this. This one is the natural log of 1 plus x. Let me double check. It's this one right here. Yeah, this one is the natural log of 1 plus x. So that's that one there that you'll manipulate. And then, oh yeah, find the exact value of the 47th derivative. Okay, well, very nice. I'll do something similar, and then we'll be done. It's not bad. Here, I'll show you what I mean. Okay, so arctan of, let's do 5x, just to be different. So I'm going to use the power series representation for arctan, which is -1 to the n times this 5x to the 2n plus 1 over 2n plus 1. So that's the power series representation for this thing. Now here's the thing, is that if you want to know well, it turns out that the derivatives, so, you can't see this. Come on, don't let me do this. There, arctan of 5x, is that better? There, you gotta clue me in when I'm being stupid. Okay, so if you remember where this came from, the Taylor series and Maclaurin series is built from a bunch, it's just a bunch of terms. So if I want to know if this is called f, we'll call that f. If I want to know let's do the 50th derivative. The 50th derivative, if it's 0, what you would do is you would look for the 50th term. So we go look for that 50th term. Oh, there is no 50th term because these are all odd here. So I guess I need a different number here. We'll make it 51, just to be different than the problem there. So the 51st derivative, what you would do is you would keep going through this series until you got to this point. You would find f 51 of 0 over 51 factorial, sorry about that, times x to the 51. Just a minute, let me put in the previous term. And the one before that, just so that you can sort of see, this will be x to the 49th, etc. So 49 factorial. Anyway, so if you were to write this out, when you got to the x to the 51, you would have this as the coefficient. So let's just do this. We have f to the 51 evaluated at 0 over 51 factorial should equal what you get when you get to x to the 51 here. Now x to the 51 comes from when n is 25. So I need to use n equals 25 for that. So I'll do this, -1 to the 25th times 5x to the 51 all over 51. Oh, sorry, that's going to be 5 times, oh yeah, I want the coefficient, so this is going to be x, I'll just put the x to the 51 here. Okay. So now I just have to clean this up and do a little bit of algebra. So check this out. We get f to the 51st derivative evaluated at 0 over 51 factorial should equal negative, because negative 1 to the 25th is negative 1, 5 to the 51st, all over 51. I'm going to drop the x to the 51st power because I only care about the coefficient. Now I'm practically done. The last thing I'm going to do is this. F to the 51st derivative is going to be negative 5 to the 51st times 51 factorial over 51. There it is. Whew. And I'm guessing that this will let me type in this like this. Let's see. Yeah, so they've got a 46 factorial here. Yeah, you could cancel some stuff here, but it'll be similar to what I just clicked on and showed you. So hopefully, is that it? Is that it for the homework? I think that's it. So the preview of the homework is done, but you can always bring your questions next time. Now, before you take off, I need to show you one more thing about our webpage, because I added some stuff this morning that is exciting and terrifying at the same time. So I dug through my files, and I found some test samples to give you. Now, we're not having a test 4 here, so I just thought, well, test 4 sample, you can lump that in with the final exam sample. So this is the practice. I don't know, this one isn't the one that I was thinking of. So you can see this is, it says test 10, whatever. But anyway, you can see that it is similar. Why can't I go backwards? Now I can. Similar to stuff that we've been doing. Let's see, test 4 practice, is this? No, that's pretty reasonable. So it's more stuff that you recognize, hopefully. Let me back up one more and take a look at the last one, final exam sample. I just want to make sure. Oh, I know, maybe it's this one. Is it this one that's crazy? One of these looked really crazy to me. Ah, yeah, that's it. Okay. I don't know where this came from, but I was digging through my files looking for practice problems for you, and I happened upon this nasty thing. So, there's no way I ever gave this as an actual exam. I don't know why this is so ridiculous, but I mean, look, I had to go to double letters apparently here, and same thing goes down here. So I don't know that I would look at this much, but if you really want lots of practice problems, this has, I think I concatenated a whole bunch of, it's ridiculous, all of those summations. So if you need extra practice, you can look at that, and I don't even have answers to it. You'll have to come to me for answers. So use this as a last resort for your study purposes, and use the other ones. But I just wanted to make sure you are aware that those have appeared online this morning for your enjoyment. We will talk about this more on Friday and Monday, probably, because your exam is what, on Wednesday? Is it Wednesday or Tuesday?
Wednesday.
It's Wednesday. So it's Wednesday at like 7:50. So there's that. I'm going to stop the recording if you want to come up and beg for mercy for, do I have anyone's exam paper here? If you don't have your exam, I probably have it here. Maybe I don't. I'm going to stop the recording though, just in case.